So good morning, everyone. Welcome to the second Distinguished Lecturer series this year, this one on this semester, second semester. Before I start and introduce the speaker, I would like to remind you that you will have to swipe for every single lecture. So downstairs, Ryan and Rosie, you can swipe to make sure that you mark your attendance for these lectures. Unfortunately, the setup is so that you have half the class downstairs and half of you are here. So there is a microphone working downstairs as well that you can ask questions that the speaker will be able to hear up here. I would also ask you, just out of courtesy to your colleagues, that you don't just stay all day up here, that you actually try to mix between the two rooms so that you get some people have the chance to also be up here with the speaker. Okay? We'll try to make it as efficient as we can, and probably Jane can also come downstairs to engage with some of you that are downstairs. Okay, to talk about, so it's a pleasure to introduce Jane Hillston, professor in Edinburgh, to come and give us this distinguished lecture. So before that, let me tell you a little bit about Jane. I find Jane extremely inspirational throughout the years at Edinburgh. And so she started off studying mathematics in '85 in the University of York. Then she moved to the US to do an MSc in mathematics as well, University of Lehigh. Then she came back to the UK, worked in industry for a while, and then decided to do a PhD in computer science. So she went to Edinburgh, started doing a computer science PhD there. At that time, so this is in the 90s, there was a lot of interest in trying to model and understand whether you could evaluate the performance of systems in a way. So there were approaches available for doing that, and there were queuing networks, there were different approaches on extensions of Petri-nets to be able to do that. And then there was at the same time also a trend on languages that were called process algebras, that were nice and compositional, that they could describe concurrent systems in a nice way. And what Jane did as part of her PhD was actually bring those two things together. And she developed a new process algebra as part of her PhD called PePa, that ended up getting a recognition as she got a Distinguished Best Dissertation Award in '95 for her PhD. This is an award that is given out by the Council of Professors and Heads of Computing, together with the British Computer Society. So this was in '95, and years later, again for her work on PePa, because PePa had then suddenly become also extremely widely used internationally, so created a lot of research impact, and she got another award for the work that she'd done, and that was the first Roger Needham Award that was given to her at the Royal Society in London. This was in 2004. She's also been, in the meantime, elected as a Fellow of the Royal Society of Edinburgh, and she is very research active, very passionate about the research she does. The way that PePa has evolved as well to bring to new, to explore that to different application domains as well, so a lot of emphasis now also on systems biology and so on. So she will be talking about, so the series of lectures will be initially about PePa, but also about the applications and the things that moved on ever since her PhD originally with PePa. So work on linking that to how do you... So one of the key things about languages that are process algebra based is the notion of compositionality, and that to use the strength of that compositionality. So when you know the structure well, you can reason about that. But when you then... What do you do if your system adapts and wants to change dynamically? So there's an adaptation how to deal with that. And also, these days, a lot of behavioral uncertainty in certain systems that you may want to understand better. How do you cope with that? So the extensions of her work are addressing that. And I hope you enjoy this series today and that you ask lots of interesting questions from a very inspirational speaker. Okay, Jane?
Unfortunately, my laptop went to sleep during your introduction. Okay, so good morning, everyone. It's a great pleasure to be here, and good morning to the people downstairs as well. It's nice to see the faces up here. I hope to see some of you downstairs later in the day. So as Juliana said, I'm going to talk about PePa, which is a language that's been around for about 20 years or more now. But then the next two lectures are actually about more current work, partly because I thought you'd want more current topics, but also from my point of view, it's much more interesting to talk about more recent work than the old work. So this first lecture on PePa will set the context of what is a stochastic process algebra, what's it's intended to do, and how do you design a language at a very high level. And then we'll go on to how languages need to be adapted to deal with other applications in year next two. So I'm going to start by giving you an introduction to performance evaluation, because it may not be something that you've covered already. And then we'll talk about stochastic process algebras, and in particular the structure operational semantics. And then we'll talk about different ways of interpreting languages, of how, when you're doing an agent-based model, how detailed do you need to be? Do you really need to understand individuals, or sometimes can you shift populations? And I'll show you the mathematical advantages of changing those perspectives. We'll do a very small case study, just so you get used to the language, and then just some conclusions for this first hour. So performance modelling is modelling of the dynamics of systems. You're perhaps more familiar with things like functional modelling, where we look for the correctness of systems. We want to know what are they able to do. With performance modelling, we were interested in things like timing and probability, because we want to ensure that the resources in the system are used in a fair way and in an efficient way. So this will typically be a trade-off, because users are happy to have as much resource as they can get. So performance problems are usually due to contention for resources. But system managers don't want their resources, which are often expensive, hard to maintain, to be idle. So they want them to be efficiently used. So you have this trade-off. But from the user's point of view, you put in as much resource as possible, and from the system manager's point of view, you want to minimize that, to keep systems simple and maintainable. And so we do performance models to try and work out the optimal, in some sense, trade-off there between the two interests. Performance modeling goes under many guises. It's sometimes called capacity planning. So we might have a server, and we want to know how well it's going to scale. So if we're going to have a 10% increase in our business, we're going to have more clients, will we still get reasonable response time? You might think, well, response time doesn't matter. Companies like Google have done experiments that show a 1/10 of a second makes a difference to their revenue in terms of loading pages and then getting click-throughs. So response time is really important. System configuration, so when you're setting up mobile phone networks and you've got frequency sharing, you need to know how many frequencies can you have to keep blocking probability low so that your call's not dropped as you move between cell areas. Or in a flexible manufacturing system, you might talk about it as system tuning. So you have here a trade-off that you might have a conveyor belt that is feeding widgets of some sort to a robot, which has an operating time, but there's a danger that if you make it go too fast, the robot will damage the widget. So you're trying to balance that to get the best performance out of your flexible manufacturing system. We're going to talk about performance modelling in terms of mathematical models which are called continuous time Markov chains. You can think of these as like state machines with a bit more information about timing and probability. So the basic idea is that you take a system, you translate it into a state transition diagram, and then we have a way of encoding that as a matrix, and then it's all in your algebra from there on. So far so good. And these state transition diagrams are representing a stochastic process, which is a Markov process, which has this condition that's here on the slide here. It's saying the joint probability, if we look at the history of time, the joint probability of the next step, given all the previous steps, is the same as the joint probability when we just consider the current state. So in diagram form, if we're looking at this path and we want to know what's the probability I could take this step, all I actually need to know is the probability that I'm here and the probability there. Okay, so it's what we call a memoryless process. And so we then just have this state diagram where we put in these transition probabilities. So we decorate each of the arcs with these probabilities that tell me both duration and choices. Okay, so I said we do timing and probability, but we encode it in one random variable. So when we have a choice, like here, these rates will determine, we talk about the race condition, which of these steps I take. So probabilistically, sometimes I'll go this way, sometimes I'll go that way, proportionate to these different rates. And because we've made it so simple, we can encode the whole behaviour in a single matrix, which just records these rates of moving between the states. So most stochastic processes will be much more complicated because you need to keep a clock to know the history of the likelihood of taking the different choices. But with the Markov process, all we need are these rates. We can put it in a matrix. And then, in fact, we can, from the matrix, work out a probability distribution which tells us the probability of being in each of our states. Okay? So we can look at that at what we call steady state, where we've reached an equilibrium behaviour, long-run behaviour, or we can look at it at certain times. When we look at it at steady state, what we know is that the probability is not changing between the different states, and so we can express it in what's called a global balance equation. So we say the rates coming in here must be the same as the rates going out. If you think of your probability as being like water, what you're saying at steady state is the water level in every state is staying the same. And so it must be that the rates in and out are balanced. Okay? And so because of that, we can just use linear algebra to solve and get this probability distribution that we're interested in. And we're interested in that because we can derive all kinds of performance measures from that steady state probability. So the steady state probability will tell us the utilisation of certain resources. We look at those states where it's used or not. We can work out things like throughput, and then we can also work out response times. So this all seems very straightforward, nice and simple, and it is if our systems are quite small. But the difficulty comes because usually this is millions and millions of states. Okay? And so you don't want to be building this at all. Okay, so people introduced high-level modelling formalisms to try and ease the burden of building that. And as Juliana mentioned, in the early 90s, people were using queuing networks and stochastic Petri nets as those high-level formalisms. Queuing networks have certain limitations that they only work in terms of queues, but depth processes. Stochastic Petri nets are not compositional. Okay, so the idea was to bring along another formalism that had the benefits of being compositional and formal so that we could do all this automatically without having to build those networks ourselves. So if we think of doing performance modelling, there are several steps. We have the model construction, and I've said high-level formalisms can really help us with that, and we generate the underlying Markov chain. Quite often, even when we do that, the matrix is too big. Okay, so current state-of-the-art tools can cope with up to about 10 million states. So that's a 10 million by 10 million matrix. Of course, we use sparse representations and other compact representations to get to that scale, but that's often not big enough for the systems we're interested in. And so we carry out various steps that we call simplification or aggregation to actually change our model. So we describe it how we believe it to be, and then we change it mathematically to get something more tractable. And then we go through the solution. Okay, so these are the kind of steps that we're interested in, and so we're interested to see whether a high-level formalism supports those different steps. So as Juliana mentioned, at the time when I was doing my PhD, process algebras were a hot topic of research, still are quite a hot topic of research. There are many, many different process algebras around. They were instigated in the late 70s. Robin Milner and Tony Hoare were the two, I guess, first proponents of those. And they're about, so their languages are called CCS and CSP, and the C is communication for both of them. So they're really about interaction between agents. And they were designed at first to give semantics to concurrent programs. So the key idea is that we have agents who engage in actions. And by tradition, agents always have capital letters. Actions are lowercase, either Greek or Roman letters. And so we have a component that here, when it's in the blue state, it can do an A. When it moves on, it goes to the red state, where it can do a B, and on to do a C or a B, and then this is our general process. So this is the idea, that we just record, as I say, it's like a state machine. We're recording what actions are possible in which states. But it's compositional. So whereas a state machine would be completely flat, we have a number of these different agents, and we can specify how they communicate with each other. And then what we do is we have a process algebra model. We have some formal semantics, which I'll explain further shortly, and they generate a labeled transition system. So that will be something like this. We went from the blue state to the red state to the green state. We could do A, B, and then in the green state, B or C, and that would be our labeled transition system. So it's just recording the possible evolutions of the system. And so these were very popular, had a lot of work. As Juliana said, people tried to exploit the compositionality to break down the problem of solving systems. So a very simple example, which we're going to use throughout this lecture, is some processors and some resources. In the first case, just a single processor and a single resource. The processor has two tasks to do, task 1 and task 2. But for the first task, it needs to use a resource. Okay? And after the resource has been used, it needs to be reset before it's available for use again. So we can describe this is called a prefix. It just tells us the first action here is task 1, and then on processor 1. Processor 1 does task 2 and goes back to being processor 0. And similarly for the resource, we do task and reset and come round again. And then we can say these are in some way interacting with each other on task 1. So they constrain each other's behaviour, that they can only do task 1 together. And so using the structured operational semantics, which I've not shown you yet, we would be able to get, but it's very intuitive for this case because they're all just sequences. We can only do task 1 together. They both change state. Then they have their separate states and they interleave. So we either get reset, then task 2, or we get task 2, then reset, and we come round again. Okay, so that's a labeled transition system. So the idea of stochastic process algebra was just to add in some more information. If we want to study timing and use of resources and fairness, we need information about that in our models. And the simplest way of doing that is putting in exponential distributions with each of our actions. So we want to bring this formal and compositional approach to things like finding throughput, utilization, and response time. So the change in the language is really quite minor. Okay, so whereas previously we just named our actions, now we give them a name, but we also give them an associated rate, and we make that an exponential distribution because we want to get a Markov chain. And then we have our components, so we tend to call them components rather than agents. And so the language can now be used to generate a continuous time Markov chain because we have the language. We're going to give it some semantics, which will give us a transition system. I'll come back to the multi in a moment. But it's a transition system, which is essentially just the state transition diagram that I wanted for my Markov chain. Remember, I wanted the states and the way I can move between them with the rates. And I've got all that information from my description. And so then that gives me my continuous time Markov chain encoded as a matrix. And I can do my linear algebra and find my performance measures. Okay, so why do we have to say multi-transition system? So if we think of a pure process algebra, and I have a component that can do walk downstairs one way or walk downstairs the other way, the end result is just you've walked downstairs. And with a pure process algebra, or classical process algebra, we're only looking at the capability. What are you able to do? And so we reduce that. So if we had a process that's A dot P plus A dot P, we just say that's equivalent to saying I can do A dot P. But when we have the timing information, and we're saying I can do A dot P at rate S, and I can do A dot P at rate S, so I've got a choice of doing it two different ways but at the same speed, then the net effect is I do it twice as fast. Okay, so we have to take care to keep track of how many times we can make a transition. It's not enough just to see what the capability, we have to also look at the rates. Okay, so what do we gain by doing this? So there's lots of work, as I said, with classical process algebras looking at what's called qualitative verification or correctness of systems. So people are very interested about reachability. Can I reach a particular state? But now we have the information that we can say how long will it take for the system to reach a state of interest. The thing to be aware of, that answer will not be a single number. It will not tell you it will take 2.6 minutes. It will give you a probability distribution that might say, well, after 2.6 minutes, there's 0.1 chance that you've reached the state. But after 10 minutes, there's 0.9 chance that you've reached the state. So we're getting probability distributions because it's a probabilistic model. Similarly, we can carry out model checking, where we look to verify a logical statement against the behaviour of our system. And so we can ask whether the property holds within a system with a given probability. So if we're looking at steady state, then that really is a fixed probability. We can just say, yes, this holds in 50% chance, say, in steady state or not. But we can also say, given a certain starting state, how long is it until the property holds? And again, we would get a cumulative probability distribution over time. Okay, so we've enriched the kind of investigation of systems that we can do. We're no longer just asking what's possible, we're putting some timing and probability information into that. So PePa is a particular instance of the stochastic process algebra. There's a number of different ones, and at the end of the lecture I'll explain the relationships between those. But I'm going to focus from now on just on PePa, which was the first, and it has a very small syntax. Okay, so these are the possible operations that you can have in the language. So this first one we've already seen. It just says, what I must do first is an alpha at rate f, and then I'm going to be a p. Okay? So we say f here because we do allow these to be functions. So it may be just a rate, or it may be a function on the current state of the system that allows us a certain amount of adaptivity. We have a notion of choice. So choice means I do one thing or another, and we saw that with the Markov chain. That's a race condition. So that's a probabilistic choice depending on the speed of the first actions of P1 and P2. Our compositionality comes from this operator here, the butterfly, which I must say was an idle afternoon of my PhD messing around with LaTeX to find a pretty symbol. I kind of just regret it now because lots of people send me emails saying, how do you make this symbol? It's actually a family of operators because it depends on that set L. Okay? And what L says is these processes are constrained to work together on all actions that fall in the set L. Okay? So anything else, they can work independently. They're just in parallel. But like we saw with task 1, they must do that together. Okay, so if one of them's not ready, the other just has to wait. Okay, so that's what we call cooperation. We have a notion of hiding, that we might want to make some things not visible. We may not want to cooperate with somebody on a certain action. Okay, so in that case, we can hide it, and then even if there is a constraint that says that action has to be shared, we can do it on our own because it's no longer visible. And then finally, we have constants that let us just name things. So typically, we're looking at recursive behaviors of agents. So we name them, and we just have recursive definitions. So a little bit of syntax that's going to be useful in examples. When we have an empty set here, so P1 and P2 do not constrain each other at all, we write it as pure parallel. Okay, so they're just working in parallel with no constraints. They can just do their actions in whatever interleaved way they want. And when we've got large numbers of entities, so sometimes we have multiple copies, so for example, if we're modeling a client-server system, we may well have 100 clients. We don't want to write them all out, so we use this notation, and we would just say client square bracket 100, or in this simple example, P square bracket 5 means I've got 5 copies. They're independent of each other, but they're going to be in a context, presumably, where they're competing for some resource. So PePa is given us semantics in what's called Plotkin-style structured operational semantics, or small-step semantics. So you don't need to worry about this too much, but it's just to convince you I have a very systematic way of building those labeled transition systems. So the way to read these rules is that if we can make whatever transition is above the line, then we can infer the transition below the line. So the prefix is the primitive of the language, and it has nothing else. So whenever we see an expression, a bit of syntax like this, where we've got alpha, comma r, prefix E, we know that we can do an alpha R at rate R and evolve to be an expression E. Okay, so that's kind of bootstrapping our whole process. Whenever we see that, we can do it. When we know that we've got an E that can do alpha R and become E prime, then if we have a choice that has E on the left-hand side, then that can resolve to just be E prime. Okay, and similarly F. Okay, so that's our just choice. We don't need to worry about that race condition. It just falls through into the Markov chain. Okay, so we'll get transitions with the different rates on, and the race condition is happening in the Markov chain. When we have the cooperation and the action type is not in the cooperation set, remember these are just purely parallel, then if E can make its transition when it's in parallel with F, but not constrained to cooperate on alpha, then it evolves on its own and updates its state. And similarly for F. We have no possibility here that both E and F change at the same time. And this is because they're operating under probability distributions, and the probability that they both want to make the action at exactly the same time is 0. So we have what's called an interleaving semantics. If things are not working together, they have to take turns. One goes before the other. We don't have what's called a true concurrent semantics, which would say that if these are independent of each other, you would have a chance that E prime and F prime both happen. Well, the transition happens so that they both evolved. We don't get that with continuous time Markov chains because of conditions in the probability. So the only way that they both change state is when they're cooperating. Okay, so we have like task 1, so if this would be like our processor can do task 1 and our resource can do task 1, then we have the possibility that they both do it together and update their state. And the thing is, we have to be careful then about the rates. And this looks a little bit horrid when you look at this. You're thinking, why is it an expression like that? It's not as complicated as it seems. So when we're looking at the cooperation between timed actions, there's lots of different answers. And in fact, there's whole papers written about the choices that you can make in designing a language to do this. So some languages restrict and say, oh, you must always have one partner be passive and have no idea about time, and the other one be active. And then it's easily resolved. The active one determines the rate. Okay. And we do that sometimes in PePa. We use a special symbol top to say, this component really doesn't care. It will go with whatever rate the other component has. There are certain functions that you need, or algebraic properties that you need to ensure that you've got compositionality. As I say, there's papers written about this. Product is one that works, so some process algebras use the product, although that's very hard to justify because the product of a rate is an acceleration, so it's kind of a little bit weird, but some languages do that because it works algebraically. What we do in PePa is that we talk about apparent rate. So we say that you work at the apparent rate of the slower partner. So if I was walking back to the department with Juliana, she's much taller than me, and so she walks faster than I do. But if we were walking together, if we were cooperating, she would slow her pace to go at my rate. Okay, and that's the kind of idea. So we assume that components have bounded capacity. I cannot walk at Juliana's natural rate, my bounded capacity, but if we're cooperating, we do it at the same rate. And that's the principle we use in PePa. So that explains why we get this minimum here. So it's really just saying, E has a notion of how fast it can do alpha, F has a notion of how fast it can do alpha, and so the rate is the minimum of those. So why do we have this bit on the front? Well, because E may have several different ways of doing alpha, and we want the relative probabilities to stay the same. We'll see an example in a moment that will make this clearer. So the rate, so we want that it's choosing this particular case of alpha with R1 is the fraction of which of R1 with respect to its total capability of doing alpha. Okay, and similarly for R2. So we're just keeping the relative probabilities the same. Okay. But for the moment, you can just think of it as being the minimum, because in most cases, that's what it is. Hiding just means that we change to this special symbol tau, which says this is a private action. Okay? And then private actions are not involved in any synchronization. And then constants just mean that we assign the behavior of a previous definition. So the language is very simple, but quite powerful. So if we go back to our processor resource example, this is just the same as before, but now we've added some idea of the rates, and we're using PePa syntax, so we have a cooperation here. And so then we can get our labeled transition system. It's as before, except now we're labeled not just with actions, but also rates. Okay? And our rate is the minimum of the rate at which processor 1 thinks it can do task 1, and the rate at which processor 0 and resource 0 thinks it can do task 1. Okay, so we just choose the slowest one, the bounding capacity. And so we can then just encode that in this matrix, which essentially is our Markov chain, and then we could find out, for example, the utilization of the resource. So what do we gain? Well, when we're building models, we've now got this compositionality, which lets us build the models up in terms of their different components. More, we can actually reuse components, so we can take submodels, and often the models are easier to understand than, for example, a PetroNet, where you have to model the whole thing all at once. We can use equivalence relations, which are formally defined in terms of language, but I'm not going to talk about today, to give us ways of reducing the model. And aggregation techniques on something that's called lumpability, which lets us reduce the models to a smaller Markov chain. We'll talk about that a little bit. And then the formal semantics can let us identify certain classes of models that are easy to solve or have certain properties. Whereas previously, quite often, these had to be done by characterizing the matrix. So there's various results about Markov chains that have particular properties, but you have to work out the block structure of the matrix, which can be very difficult to do if you're talking about a million by million matrix. We can do it syntactically and have tools just identify it right from the start in the language description. And there are complementary logics that also work and let us do model checking on these models. So I want to go and think about the semantics a little bit more. So under the structured operational semantics, if we've got a stochastic process algebra model of a number of different components, we generate the continuous time Markov chain. This then gives us all the interleaved actions, so what might be quite neat components can lead to quite messy state spaces, which is determined by the local states of each of the participating components. When we model as an individual, we really think about each individual as itself. So in this particular case, we're assuming that we care whether it is this processor that's on the furthest left that takes part in the cooperation, or the one in the middle, or the one in the right, and similarly which resource it is, the one on the left or the one on the right. And when we do that, that's when we start getting these fractions in our cooperation rate, because we have 3 ways of choosing which processor to involve in the cooperation, and we have 2 ways of choosing the resource. Okay, so we have 1/3 for the relative probability of this processor, and 1/2 for the relative probability of this resource. And so we get this as the rate for each of these. So the total capacity will be the minimum of 3 times the processor, so that's the capacity here, and 2 times the resource, but then each of them has a relative probability, keeping the normalization of the probability distribution. But generally speaking, we don't actually care if it's this processor or that processor. We actually only care if it's 1 processor in use or 2 processors in use. So we often kind of abstract from that. But assuming for the moment that we keep the full representation and the size of the state space is not too big, then we can do the numerical solution, as I already hinted. And this can give us the steady state or the transient probability. But the state space will grow very fast if we pay so much attention to individuals. So if we look at this very simple case, we looked first at the case where we had 1 processor, 1 resource, and we saw there were 4 states. If you have 10, and 10, and you just leave them all as individuals, so you really care whether it's the processor on the furthest left or the one on the furthest right or one in the middle, then you quickly get to 1 million states. Now this is a trivial system. Even if you've got lots of copies of the different things going on, it's not very interesting. And my tools can only cope with 10 million, so you can imagine we don't want to do this. Okay? If we've got 10 copies of the processor, we really probably don't care that much which one is doing the work at a particular time. And so we give up the identity of our processors, and we just treat them as a set of processors, and we just count how many of them are really engaged. And this is what's called aggregation. So we make the counting abstraction and just say, well, I'm only interested in the states where 2 of the processors are in use and the rest are not. And that will actually be when we have 3 processors, there's 3 different states like that, but we don't care which of them, just the case where we've got 2 of them in use. The way that we design the states in PePa is very syntax-based, which makes it great for humans to read the models and understand, but not so good for doing things like aggregation. So we also switch to a more numerical representation of the states, and then we can really do both this aggregation and some other things as well. So if we're looking at this example again, then we can say actually all those states on the right-hand side are equivalent. In each case, one processor has cooperated with one resource and moved on to the next state. And so we actually say, well, we started where we had 3 in the state P0 and none in the state P1. And we had 2 in the state R0 and none in the state R1. And then I make a transition and I get to the state where I've still got 2 in the state P0, but I've got 1 in the state P1 with possibly different ones. And here I've got 1 in the state R0 and 1 in the state R1. So that describes all these different syntactic forms in a more abstract way, and lets us just treat this as a single state. So it's much more compact, and now we just get that minimum rate, which we saw before was we only had to do that renormalization when we were splitting out all the individuals. And there are lots of algorithms that let us do this. If we go down to the graph level, if we want to build the label transition system, we can use an algorithm called, for example, Page and Tarjan, which is very good at finding the maximal partition according to an equivalence relation. But in practice, we'd rather do this directly. And the good news is that because PePa is a process algebra, we can do this component by component, which is much more efficient. So we can look at each component and reduce it. We can look at the processors and reduce those. We can then put the reduced processors with the reduced resources. And so we can tackle this in a much more bottom-up kind of way, whereas the previous approach using the algorithms would mean you had to build the whole system and then reduce it. So we first did this using canonical forms of just looking for when things were equivalent by syntactically changing them. But as I say, more recently we're using these counting abstractions and get much more compact. So we say these are not individual-based models because we don't really care about the identity of the individuals. Sorry, they are individual-based models because we still keep the notion of individuals, but they're not identity-based because we've given up knowing whether it's the one on the left-hand side or the one on the right-hand side of those resources. So that's what we call aggregation, and it's formally an equivalence relation in the process algebra, and as I said, can be automatically applied. Even when we do that, we often end up with models that are too big. You saw how easy it is for the state space to blow up, and then we will resort to stochastic simulation. Stochastic simulation of Markov chains is very efficient because of the memoryless property. You don't need to keep an event list. Every step you can just look, what action can I do now? So the difficulty just comes that each run is just a single trajectory through the state space. And as your state space gets very big, your trajectories need to get long in order to really sample all the different possible behaviours. What's more, you need to do many runs in order to get an average behaviour, if you want to know what's a typical or average behaviour. So here's our example again with 100 processors and 8 resources this time. So this will looks okay, looks so maybe it's kind of reaching a steady state here. But then we do another run, and it's actually quite different. Okay, so just single runs, and then another one, and then another one again. So we have to typically do many runs before we can really see the characteristics of the behaviour of the system. And so this is 10 runs. Oh, later I have 100 runs. But 10 runs, you start to see a pattern. And you see that actually the first trajectory I showed you was quite anomalous. It was very different to the typical behaviour. And that's why you always have to be careful with simulation, because any run might be anomalous. So for some SPAs, we can go even further if we start to think about things in what we call collective dynamics. So we stop looking at individuals at all and start to think about populations. So we see collective dynamics, for example, in traditional models of disease spread. So you've perhaps seen what are called SIR models, susceptible, infected, recovered models, where you just look at the population and how the disease kind of flows through the population without caring at all about individuals. You just care about the proportion of the population who currently have the disease. That might seem a long way for computer systems, but actually when you're doing things like scalability analysis of client-server systems, you can take a very similar view. You perhaps have a population of servers, typically quite small, and then a very large population of clients, and what you want to know is what proportion of the clients are getting served. So we shift to this population dynamics or collective dynamics view. So we lose both the identity and the individuality in this case. So this can happen when we have components which have typically quite a small behaviour themselves, but we have a compositional structure that shows how the components are interacting, and we have large numbers of individual components of a certain type which can be regarded as a population, so like those clients. And then the interactions of the population groups lead to an emergent behaviour at the population level. So this shift in perspective lets us use different mathematics essentially to model our system. So our systems can be much larger than we can deal with simulations, because we no longer collect any information about the individuals. We lose some information, but we can tackle bigger systems. We focus purely on the count, but we know how to do that because we've done that for the aggregation. But the key step is we stop treating them as discrete systems and start treating them as continuous systems. So we have a discrete state space, let's say it's quite a small one like this, and we make steps between those different states. That's clearly something where we, and this is always what happens in a PePa model. We kind of go up or down by 1 in each step. So we change processor 0 to processor 1. So our count of processor 0 goes down by 1 and our processor 1 goes up by 1. But as we get a bigger and bigger population, proportionately the influence of each step gets smaller and smaller. And so it starts to make sense that we could just approximate that by a continuous flow. So we don't look at individual steps, we look at an overall flow between those states or between those proportion of states. And we get a semantics in terms of ordinary differential equations. So we look at our processing resource example. What we can do is analyze what's the impact of each action on our agents. Okay, so we can see task 1 decreases processor 0, it decreases resource 1, but it increases processor 1 and increases resource 1. Okay, so it's just a very straightforward syntactic analysis of the model in this case. We can do that, and then actually we can translate those ideas of increase and decrease into terms within an ordinary differential equation. So we introduce, sorry, I should have pointed that screen. We introduce a variable x1 and say, well, it's decreased by this action task 1 and it's increased by the action task 2. Okay, so if we're looking at processor 0, decreased here, increased here, we can see the rate here is going to be R2 times the number of processor 1s we have, which is x2, and then the rate of this one is going to be that minimum, again influenced by the number we have taking part. Okay, so I'm not going through this in detail, I'm just trying to give you the intuition. This is all, again, actually encoded in a structural operational semantics, just like the one we saw earlier, but I'm giving you intuition of how it works. So we can derive a set of ordinary differential equations for each of our different process terms, and now we can solve this system in fractions of seconds for any number of agents. So if we go back to our 100 processes and 80 resources, this is 10 runs or 100 runs of the simulation, or even 1,000 runs of the simulation, and then that's the ODEs. So what the ODE does is it gives you really the trajectory of the average behaviour with a large population. In this case, 10 and 80 is high enough to be a large population. If we did the ODE with, let's say, two processors and one resource, the result would not be so good, because there each step is making a big change in the proportion of behaviour. But once we get big enough that each step is not having a huge impact on those proportions, the ODEs give us a good approximation, which is much more efficient and gives us much greater scalability. So we sometimes use this for client-server systems when we look at scalability, because the simulations would take days, but the ODEs will take seconds. So to wrap up, I just want to give a simple example, and it is really a very simple example. I've cut it down to be quite small so you can really see the components and how they work. So this is actually a simple model of a location tracking system. So the idea is a smart building with sensors in the walls, and you know where this came from, and active badges or RFID devices on either people or equipment. They use these kind of systems in hospitals to track where certain pieces of equipment are. So in our case, we're assuming that active badges worn by people, and they each transmit a unique signal, which can then be detected by the sensors and reported back to a central database, which is kind of keep track of where things are. So there's a lot of trade-offs in this system, because the badges are battery-powered, so you don't want them to be broadcasting their location too often, because that will mean their battery runs down. So we want to trade off the battery power versus the accuracy of the information that's harvested. Because obviously if they don't broadcast often enough, then we may not actually know where things are, because sensors may completely miss some of the updates. We will also have the possibility that different badges collide, and if that's the case, we assume that the badge sleeps and randomly, after randomly determined time, we'll try again. So this PePa model here is just tracking the progress of one badge wearer. If your real system would have obviously much more, and just 3 connected corridors. And these are numbered 1, 4, 1, 5, and 1, 6. And Juliana knows who the badge wearer is. And the activities that are performed in the system include the badge registering with the sensor, which happens at some rate r, person moving to another corridor, some rate m, and a sensor reporting back to the central database. So we assume we have no control over the rate at which people move. That's just something that happens. But we have at our disposal the parameters of the rate for the registering and the rate for the report back to the database. And what we're interested in looking at is the probability that the information in the database actually matches the position of the individual. So for our individual here, you can see that they can be in each of the corridors, and they're just named according to which corridor they're in, P14, 15, and 16. And when they perform a random walk, basically, these are in a row, 14, 15, 16, and back again. So in 14, they can only go to 15, in 15, they can go either way, and in 16, they can just go back to 15. So that's this part. It's just the random walk of the badge owner, and then randomly And in competition with that, they're registering. But we assume that the registration is faster than people moving, that they're not just walking about, but they're actually spending time in these different locations. And so we have the registration rate here, which is the same for each of the corridors and each of the sensors. And then our sensors, now this is the case that I mentioned, where we say, actually this guy doesn't care about the rate. He has no control about the rate at which somebody's going to come into the corridor. So he's passive with respect to the rate of the registration. So that's what this top symbol means. I have no idea of what rate this happens at. So if we think of minimum, everything else is less than top. So it means this R will determine the rate. And then he sends, once he's received a fresh update, the sensor sends it to the database. And our database, in fact, is completely passive. It just accepts updates and then updates its record of where that person is, so whether they're in 1.4, 1.5, 1.6. As I say, this is a really small fraction of the model, but it just gives you a very small intuitive example to look at. So those are our three components in this case, or, well, with multiple here of the different sensors, so strictly speaking 5 components, but 3 component types. So we start with the person in corridor 1.4, and we assume that the database is accurate, so it has a record that they're in 1.4. And then we have the 3 sensors in parallel. Okay, so if we look at this, we call this the system equation. It tells us the structure of our system. It's saying the sensors do not interfere with each other at all. Okay, they just happen in parallel. But the person is constrained to interact with the sensors on these actions from registration in 1.4, 1.5 and 1.6. And what's more, the sensors are constrained to interact with the database on this report 1.4, 1.5, 1.6. Okay, so this is the structure. And this is typically how we do it. We build our components in a kind of case-by-case way, so it's quite simple to build our models, and then we put them together, and we could change this. We could have another person, so we might have Q moving around 1.4, 1.5 and 1.6 with slightly different rates, and then they would also be interacting. We'd add more actions for cooperation. And then we can run this model, and this is a small graph that we've got in this case, looking at the probability that the database holds inaccurate information. And it's depending on the rate S with which the sensor sends the information to the database, and R, the rate at which the badge is sending the message to the sensor. So as you would expect, as these get slower, then we've got more probability of inaccuracy. It's not very high, it gets up to nearly 0.2, 1/5. And then you can look at this. Now, I haven't actually put in the calculation of energy use, but you can do that as well with what's called a reward. So we can look at each state as how much energy is used. And so you could then also decorate this with the energy use and look at the trade-off between the probability and the probability of accuracy and the energy use or battery life. Okay, so what I've told you is just a very intuitive overview of PePa modelling. I hope I've motivated for you as to why it's interesting and useful. And in particular, I've talked about 3 different ways of interpreting our models. So we have one formal description language, but different semantics in terms of different mathematics. So we had the first explicit state here is the individual-based view. Okay, of just really looking at every component, every state of every component, and we build a complete continuous time Markov chain. But often we want to shift away from that individual view to really looking at identities and use the counting abstraction instead, and we get a more aggregated continuous time Markov chain, which allows us to study bigger systems. And then in the extreme case where we really want to study very large systems, we move to using the fluid abstraction, which is what we call a continuous approximation of the continuous time Markov chain. So it's always got a continuous time Markov chain semantics, but then we sort of map that to different mathematical structures to do our analysis. So we have the full generator matrix, the reduced generator matrix, or the set of ODEs. There's a tool if you want to play around with this. So it's Eclipse plugin. So if you have the Eclipse system, you can just download the plugin, and it looks like lots of other Eclipse tools. We have an editor window, we have some results down here. This is showing a state space. This is an example actually of the virtual university where you're looking at students registering for courses and the efficiency of that. And it's a really quite robust tool now. It's in use. If you want to go and try it, there's a little video to show you how to install it. And we're very happy to have users. As Juliana mentioned, we have users all over the world, including Brazil with Ricardo, but also people in Poland, in China, in Russia. We still get emails of people sometimes asking questions, most often asking questions, occasionally saying thank you because they've done something interesting. So although it's been originally designed particularly for studying computer systems and to some extent communication systems, people have found all sorts of other uses for PePa, and quite often we only find about this after the fact. So this one, locks and movable bridges, was one where they actually mailed us afterwards and said thank you very much. It was very helpful, and they were studying the flow of water traffic in Belgium, so they still do a lot of cargo transport on the canals, and they were looking at making it more efficient by the speed of different locks and movable bridges. It's been used for diagnostics on automotive systems, in particular buses, by people in Italy. As I'll speak about more in the next, I think it'll be the lecture this afternoon, as Juliana mentioned, PePa started to be used for biological systems, and actually we made a new dialect which is better suited for those by PePa, and I'll talk about that this afternoon. And then people also looked at crowd dynamics of people moving through buildings, particularly in evacuation situations, and used PePa for that. And so it's not just performance modelling. So I said I would mention the other stochastic process algebra languages. So there are some choices you make when you design such a language. So PePa is what's called an integrated time language. You saw that we had actions that had a rate and associated with them, which means that we assume that each action takes some time. Some of the languages instead have interleaving of actions and delays. So the timing is separate. So you have two types of prefix. You either have an action prefix or a delay prefix. Expressively, they're about the same because you can always take what you would do in PePa is, let's say, I'm lecturing, that takes a time. If you were doing it in an orthogonal time language, you would say, I begin the lecture, there's a delay of the time of the lecture, and I have an action end lecture. So that's just the difference there. And then there's a difference when we're using the integrated time of what kind of delays we allow. So I've talked about PePa, which is an exponential-only language, but there are also languages that allow exponential and instantaneous. And there's also languages that don't restrict themselves to continuous time Markov chains. So they actually have general distributions, which makes life a lot more complicated because then you need clocks, because you don't have the memoryless property, and you don't have interleaving in the same way. In the orthogonal time, it doesn't make sense to talk about instantaneous actions because actions are instantaneous, and so we just have exponential or general distributions. So we've talked about PePa. Another exponential-only language is something called the stochastic pi calculus. In the exponential and instantaneous, the best language is probably EMPA, from Italy. And then in general distributions, there's quite a few. So there's a language called TIP, Spades, and GSMPA, which is Generalized Stochastic Markov Process Algebra. And then in the others, there's a language called IMC, which is quite largely used. So this is the one where you do an instantaneous action, have an exponential delay, and then your next action. And we have IGMSMP and a language called Modest, which is also quite widely used. Actually, Modest has been used by the European Space Agency for looking at some of their processes. So as I say, we've just focused on that top branch, so there are many more for you to explore if you're interested. So stochastic process algebras, I hope I've convinced you, are a useful high-level language for performance modelling, and they have many benefits. The semantics are encoded in the software, and so you just have to describe your model, and because it's all formally defined, your mathematics just gets done automatically, which is very helpful to people. Nobody really wants to build a 10 million state Markov generator matrix. There are many different reduction techniques. I've really only talked about aggregation and the fluid approximation today, but we have many different ones looking at particular classes. And the key thing is that these are all defined in the syntax of the language, which means that we can prove their validity once for the language. Whereas if you were working directly at the continuous time Markov chain level, each model you would have to prove the validity of the reduction that you do. And so it's a real benefit to be able to enshrine these kind of results in the semantics and therefore in the tools without having to prove each time you have an example model, oh, I can make this kind of reduction because it falls into the right class. And then PePa has been used, as I've mentioned, for a wide variety of applications and continues to be used. I must say I don't do very much work on PePa anymore. As you'll hear, I've moved on to other languages, but I still do some. So the most recent paper I published, which was just a couple of months ago, which was looking at information leakage for secure computations, where people can do timing attacks if they can see how long certain things, so you can inadvertently allow information to leak because certain computations take longer. So it's looking at ways to try and pad things so that you don't have that kind of timing attack possible, and we're using PePa for that. So thank you very much for your attention. If you want to find out more about PePa, there's a web page with lots of information. You can download the tool. As I say, there's lots of example models, there's videos for how to install the tool. So thank you very much.
Questions? Salim?
Thanks very much for the talk. And the idea of modelling, especially complex systems, is really useful, as you've shown with some practical examples. I wonder if you could just explain what the particular challenges are of using something like PePa for a post-hoc analysis of a real system as opposed to designing a new system from scratch, really.
Okay, so I'll repeat the question because I think not everybody perhaps heard it. So the question was, what are the difficulties? So I've talked very much, and that is very much the perspective of PePa. We're designing a system and we want to explore the different possibilities and trade-offs. But the question was much more if you're trying to do a post-hoc analysis of a system that already exists, and what are the challenges? And so this comes up very much from example for the work we do with biology, where we're trying to reverse engineer the system rather than design the system. And the biggest challenge is the parameterization, essentially, of finding out, well, if it's a computer system, we usually assume somebody knows how it works, so it's sufficient detail that we can structure the processes, but the difficulty is usually finding the rates and probabilities that are appropriate. And actually this afternoon, I didn't plan, we'll talk about process algebra that allows for uncertainty, and so then combining the formal modelling with machine learning so that we can leave certain parameters within the model unknown and then look at the data to find what are the most plausible rates for certain actions given the observations that we make of the system. So the same is true. I've not done work on that myself, but I have a colleague, Charles Sutton, who's looked particularly at queuing networks, where you're trying to do post-hoc analysis via queuing networks, and again, using machine learning to try and find the right parameters. You can also, people have used genetic algorithms, and they've used genetic algorithms for finding the structure of the models as well. Okay, so you perhaps don't know quite which components you've got, but that's very difficult. Okay, we've used particle swarm optimization for looking for configurations. So where you're perhaps looking at these scalability problems and you want to see how many servers are really being used or something like that, we've used particle swarm to work backwards and find what the configuration of the system is. But it's a difficult problem, not particularly for process algebras, I think, for any dynamic modelling to try and fit the parameters appropriately.
So for the students, as they think about maybe projects, or they go out into the world and they face these challenges and they say, I'm going to go back and use PePa. Do you get a sense of, or can you offer them some guidance about where maybe these tools just don't work? Or
So I'll talk about some of the limitations of PePa in the next lecture, because PePa is a particular style of language. We say it's a conservative language. And many modern systems now are not so conservative. And I won't go into details of that because that is in the next lecture. This race condition makes modelling very simple, but isn't always appropriate. Sometimes you want to be able to make explicit probabilistic choices, which are completely decoupled from the timing, in which case PePa is not a good language. There are many problems, but there are also many cases where it does work well. As with all formal models, it's actually quite often, as well as the actual analysis, and I like it that you can calculate things, but the process of really writing it down makes you understand the system much better.
okay, what's your favorite use so far? That you shining, you look back and you say,
Oh golly, I don't know, I like the surprising ones. I mean, when people started using it for biology, I thought that was really cool. And then I could see, actually, it doesn't work perfectly, so we need to redesign the language. I do like the locks and movable bridges, because that one just came out of the blue. Of the ones that we've done, probably some of the web server configuration models that we've done. But I have to admit, I'm more a theoretician than an applied person.
So it's been a long time since I did physics,
Okay.
but many of the optimizations you were speaking of seem to have a flavor of statistical dynamics to them. So I was wondering if you have some insights for them or they have some insights for you.
Yeah, well, certainly the fluid approximation that we do is very much based on mean field approximations in physics. I'm not sure that we've learned anything else from the physicists, but I must say my knowledge of physics is somewhat limited. But yes, they do similar things of moving between discrete and continuous. Sometimes.
And ignoring identity, for example.
Yes. So,
Yeah.
I've not had a friendly physicist to have those conversations with.
Okay. Thank you.
Anyone else? So otherwise we break now, because we already ran out of time a little bit with the beginning, with setting up everything. So we're supposed to start again at 1:15. So there's coffee and tea and lights downstairs. So